Okay, so our infamous James Bond problem. I'm sure that we've seen this problem in quite a bit of detail in the last few days, and I want you to go ahead and have a worked out solution in the event that you'd like to look at it in more detail. So James Bond must get across this 1200 meter river in minimum time, and so we're going to go ahead and try to figure out a way of minimizing this time by writing an equation as for t as a function of theta. Let's go ahead and draw a little sketch here for this problem. So here I have a 1200 meter wide river. We're going to solve this completely in variable form, so let's call that W is 1200 meters. The width of that river. James Bond, who is starting right here, must get to a point directly across the river. He can do that by rowing his boat. Let's go ahead and assume that he's going to row into the stream a little bit. We'll call that vector B, so that would be the boat speed. Turns out to be 1.6 meters per second here, but he's going to angle that boat upstream at an angle theta, yet to be determined. Now when he combines his boat speed with the speed of the river, let's go ahead and draw that in green, we'll call that C for the velocity of the current, 0.8 meters per second for our particular problem. He will have a combined speed, so his velocity relative to the shore, V, of the boat relative to the shore will be in that particular direction. It will take him downstream to that particular spot, and then of course he's going to have to run up to here. So we have two times that we need to calculate here in order for us to optimize that time interval. So let's go ahead and write t as the time to cross the river, so let's call that tb for time for boating, plus the time to run. So he's got two different intervals of time that he's going to have to complete in order to finish up that task. TB is found relatively easily, actually, with our diagram. We see that the distance he has to go across that river, 1200 meters, is really just dependent on that particular speed. Since that's the only velocity that has any component that's pointed across the river, we really just need to have that velocity. Let's call that B times, it looks like it's the adjacent side. If I think of this as a right triangle there, with that B being the hypotenuse, that would be B times the cosine of that angle. And so if I want to figure out how long it's going to take for him to cross 1200 meters at that speed, we can go ahead and find T sub B like this. T sub B would be equal to W, the width of that river, divided by B cosine theta. And that's one of my times that I need to consider, dependent on our W and B and then whatever angle we choose. Now the running time is a little bit harder to solve, so let's go ahead and see if we can't figure that out. We're going to have to figure out how far downstream he's gone, and that distance is right here. So he's gone downstream a certain distance, and we're going to have to run back here. So let's see if we can't first figure out, let's call this delta x, how far downstream he's gone. So let's go over here. Delta x would be the velocity that he has in the x direction times the time interval that he's traveling across that river. Now that time interval is t sub b. So we've already calculated that. Let's see if we can't figure out what v sub x is. V sub x is actually has two different velocities that are going on here. We have this velocity, which that's pointed that way. That velocity would be called b sine theta. Okay, so again, that would be opposite to this angle here. It'd be that vector pointed towards the right, so pointed up the river. Now the other one that's also acting in that direction is all of C. So C is pointed downstream this way. And so if I wanted to get v sub x, you notice I'm going to have to subtract these two values because they're in opposite directions. So delta x would be equal to, let's see, it looks like C minus b sine theta, and then multiplied by t sub b. Well, t sub b we found was right here, w divided by b cosine theta. And so that would be delta x. Now, ultimately, though, we're looking for t sub r. Well, t sub r is just simply found by taking how far he has to travel, delta x, and divide it by his run speed. Now, we haven't defined run speed yet. Let's go ahead and do that. Let's call that 5 meters per second. Let's call that r. So delta x divided by r. And finally, if I want to get t sub r written, let's clean that up a little bit. T sub r would be equal to, let's see, that would be CW minus BW sine theta all over, let's see, we've got B cosine theta and an R in there, so R, B cosine theta. And so there's T sub R. Another value for time that's dependent on the angle that we choose. Now, of course, T, the equation that we're ultimately looking for, is a combination of these two. So W all over B cosine theta plus this, CW minus BW sine theta all over RB cosine theta. Now, typically, a question like this might be develop an equation that could be solved to determine the minimum crossing time. Well, if I get to this point in my equation and I say I have two fractions here, I might look to see if I can't combine them, and I can rather easily. If I see that this one has a B cosine theta, that's an RB cosine theta, let's go ahead and multiply this, this fraction here by R over R. That allows us to clean this up a little bit. T would be equal to, let's see, RW plus CW minus BW sine theta all over RB cosine theta. And just for grins, I'm going to go ahead and pull out a common W there. Since W is common in each of those terms, let's go ahead and write it as WR plus C minus B sine theta all over RB cosine theta. Now, the value of doing this is that now we have an equation for time that depends on some given values, like the width of the river, the run speed, the value of the speed of the current, the boating speed. But it's dependent, the time is dependent on that angle theta. Now, when we have time written as a function of theta, we can optimize it. We can determine the angle at which we get a minimum time. And that, of course, is the goal of calculus, of optimization, is to try to write one thing as a function of something else so that we can determine how certain factors will affect the other thing. Now, our easiest way to do this is probably on Desmos. I'm going to go ahead and pull up a Desmos screen. I already have that equation, W times R plus C minus B sine theta, or sine of x, all over RB cosine of x. We have our graph that will be created over here once I define these particular things. W, we said, was the width of the river, which for us was 1,200 meters. So let's go ahead and write that in there. R was the run speed, and so R, we said, for this particular problem was 5. C was the speed of the current, 0.8. And B was the boating speed for our problem was 1.6. Now, this windows are already set up here for us. If you recall, I think we did this in class when we determined how long it would take if he just simply went right across the river. So angled his boat at 0 degrees, so he was heading straight across the river this way. He would have been pulled downstream quite a bit further, and then he would have had to run back up across the shore to get to that point. We calculated that time to be 870 seconds. Now, the other time was if he went at a 30-degree angle into the water, the current would have pulled him down so that he would have just traveled straight across the river. That value that occurred at around 30 degrees. In 30 degrees, we calculated that time to be about 866 seconds. So sure enough, those are our two values. We're, of course, interested in this value. That's the minimum time it would take for him to cross the river, 836 seconds. And that would occur if he went 16 degrees into the current. And so that particular angle would minimize our time to get across that river by going at 16 degrees, and that would take about 836 seconds. And sure enough, James Bond would be able to get across that river, defuse that bomb, or catch that bad guy, whatever the case may be.